So yeah, I'm going to be looking at remobilizing our cities after a pandemic. And what I mean by that is how can we use and leverage pedestrian modeling to look at different mitigation measures as we start to return to work after COVID-19. So the current situation, the reason I start with this slide is I think the current situation is different for everybody. I'm extremely fortunate that I am able to work from home. Both logistically, I can work from home, and even the work itself lends itself to being done remotely. Hopefully most of those watching this presentation are in a similar situation. I think we're quite fortunate in the AEC industry that a lot of the technical and management type functions can be delivered remotely. So we're fortunate in that sense. I'm also extremely fortunate that, as you can see here, I have great companies. I work from home. I've got my dog by my side all day. I live with my fiance. But again, that's not the same for everybody. There are a lot of people that are struggling through this as they live alone and as they crave some more social interaction. And so the whole point of this slide is really to show that, I am extremely fortunate. I can work from home. I do have great company, but that's not the same for everybody. And I think this illustrates the importance of just how important it is to get back to work and to remobilize our cities. And so the impact on transit, this image I took from a TransLink presentation, which they gave in late April. And you can probably apply this image to many industries as well. But what we saw was an initial drastic drop in demand. What we've heard anecdotally is some transit agencies, I think they're at about 20% capacity right now. So again, it's just a drastic reduction, and that's not viable from a business perspective. We're now going through the recovery phase, so we're starting to get back to work. We are returning to transit. We're starting to use buildings more and more, but there is uncertainty on what this final recovery is. Are we going to be back at the same level as before the pandemic hit? Or is there going to be a paradigm shift where we are working from home a lot more often? There is an overall reduced travel demand. There's just, as I said, uncertainty on what this actually looks like down the road. But what I want to focus on is really not so much the business side of things, but more if we look at our buildings and how we actually use those and what can kind of lend itself to modeling. So what we've seen from different transit agencies, this list here I took from TransLink, which is Vancouver, Calgary Transit, and then here in Toronto, TTC and Metrolinx. So just a range of things that we're seeing. In some cases, there are stations that have been closed altogether simply because they have too great a risk of large crowding. There's simply not enough room in these stations to actually have physical distancing. In other stations, we do see a promotion of physical distancing and face masks. We also see different agencies introducing one-way corridors and stairs. What this is trying to do is essentially mitigate cross-flow. So by having a one-way corridor, then you don't have people walking against each other. It's just trying to mitigate that interaction between people. The vehicles themselves, we see in many cases limited seating. In Toronto, for example, if I look at a streetcar, I think 1 in 4 seats is currently available, so you're at 25% capacity. I've been hearing on some trains and some buses, you're at 1 in 2 seats are available. So still quite a reduction in capacity on those vehicles. We're also seeing changes in schedules. This could be coming from the agency itself. So I know a lot of travel agencies have introduced new schedules for their services, but we also see people introducing their own schedules. So a lot of people, as they return to work, are going to shift to off-peak travel just to try and avoid that large surge on transit. And then more on the policy side, we see a lot more frequent cleaning. In some cases, we see safety kiosks where you can walk up, get your temperature screened, and get some input on the measures that are implemented in that specific station. But really for today's talk, we're going to be focusing on the first half of the list. These are all things that speak to how people move through the space, how they interact with the space. And for that reason, these are all things that lend themselves to modeling. If we look at buildings, similar to transit, we see a drastic reduction in the usage. Many office buildings are currently empty. I believe our Vancouver office, just last week, we returned to work. So we do see a difference depending on where these buildings are and the local condition there. If we look at other types of buildings, so museums, stadia, those also have a drastic reduction. And in many cases, they're closed simply because there's too great a risk of people being within close proximity to each other. And so if we look at this image here, so this describes the different phases of the pandemic. This is taken from the World Health Organization, but this specific version of the image was adopted by Perkins and Will in their document Roadmap for Return, which I would urge everybody to take a look at this. It's extremely comprehensive, especially for offices as we return to work. But what we can see in this image, so we've all lived through this initial phase, this response. This was when we saw the almost overnight a transition to working from home. Then as we were working from home, things kept getting worse and worse. Eventually, hopefully we're past this peak, but we are seeing eventually a transition phase. And it's this transition phase where we start to look at how are we actually going to get back to our offices? What sort of measures are we going to implement to make that safe and comfortable? And then similar to transit, there's uncertainty in the future. What does the final office situation look like, and how is that going to differ from the offices that we were used to before the pandemic? And so similarly to transit, if we look at some of the measures being implemented, so the first thing we see is the floor capacity is being determined by physical distancing. That current recommendation, I believe, is 6 feet or 2 meters. And with that in mind, you can start to lay out floors and understand how much capacity does that floor actually have, keeping in mind that people want to maintain that 2 meters between each other. In some cases, to help achieve that, we're looking at furniture being reconfigured or meeting rooms being reconfigured. Jumping ahead one, within those same floors, we can also introduce one-way corridors and stairs, again, trying to mitigate the cross flow of people and interaction that people have. If we look to the lobby, so we have the elevator, which we're going to see limited elevator capacity. There's been quite a few articles which state that the elevator is basically the bottleneck as we return to the office. We're able to plan what we do within our office space itself, but it's the elevator that gets us to and from there that becomes the bottleneck. Keeping in the lobby, we can look at designated entry and exit doors. Again, it's a way to eliminate crossflow, try to separate the two flows so we have less interaction. And then similarly to transit, we have staggered schedules, trying to spread out the arrival and departure of people so we don't have large surges in the morning and the afternoon. And then again, going down into more of the policy aspect is how do we actually clean these spaces and keep them safe. But again, it's the first half of the list where we see the actual physical aspect, how people are moving through and interacting with their spaces. And these are the things that lend themselves, again, to modeling as a way to quantify them and compare different measures. And so if we look at pedestrian modeling, the traditional use for it has really been on, I would say, any building or any piece of infrastructure where you have a large volume of people and you want to quantify how those people move through the space, which basically tells you what is the user experience like. We can then look at the travel times, we can look at densities, and we can compare that back to different standards to prove that we've designed it accordingly and it does have the desired user experience. This example here is a transit station where, in this case, we're looking at a construction stage. And so as we introduce construction hoarding, as we close off different areas, what impact does that have on pedestrian movement and what impact does it have on the user experience? We can also use pedestrian modeling in emergency scenarios. So this example here is a building where we wanted to quantify the emergency evacuation times. And in this case, we can actually model the building. We can determine the occupancy of it, basically the full occupancy determined by the code. And then for a range of scenarios, we can run the evacuation and quantify how long does it take people to evacuate. We can then compare that back to standards that are in codes, or we can combine that with an overall fire analysis. We could model a fire, say there's a fire in this floor here, and we can look at how long does it take for that floor to become unsafe as smoke accumulates and as temperatures rise, and how does that compare to the evacuation time? So the sort of analysis, we can actually run the evacuation and prove that that building is safe for a range of fire scenarios. And so these both represent what I would call the traditional uses, large buildings with high volumes of people that we want to quantify the experience for, or buildings where we want to, for emergency scenarios, quantify the evacuation time. But as we look to post-COVID and how we use our buildings, we might want to understand it's still keeping with the traditional output. So these images that I showed here, these are the visuals and the videos, and they're nice because they allow you to visualize what's happening and they allow you to interrogate the model and see if something isn't behaving properly. But really, we want to extract some sort of output from this model that we can quantify. And that's what I'm describing here, the traditional output. So along the top, we have Freudian level of service. And what this describes is really the density in a space. And that then tells you how easily is it to move through that space. So level of service A, very low density. You can basically walk through these spaces unimpeded. If you contrast that with a poor level of service, which is E or F, much more congestion, and it's a lot harder to actually get where you're trying to go. We would call that a very poor level of service. So that's how we define the different levels, but visually we can overlay that on a contour map. So what we're seeing here is a density map that basically describes for a given scenario, what is the average level of service. And as an example, we can see there's some queuing at the base of this stair. and some queuing around this corridor as they turn to enter this stair here. So it is some way to quantify the actual output that we can then use to compare back to standards. So that's on the level of service. We can also look at travel times and how people accumulate. So this graph in the middle here, what this is looking at is a train platform over the peak hour, so 8 a.m. to 9 a.m. in the morning. Or sorry, this is 8 a.m. to 9 a.m. And what the lines show, the solid lines are people arriving on trains. So they arrive on the train and they clear the platform and exit the station. And then the dotted lines we see along the bottom, these are people that are within the station waiting to board a train and then leaving the station on that train. And the different colors represent different train services. And so what this image here shows is it basically tells the story of how do people accumulate during that peak hour and allows us to understand how long does it take them to clear the platform. We can also look at actually quantifying travel times. So this image here, I believe this is for an emergency evacuation scenario, but we're able to run the dynamic model, but then extract from it how long does it take people to get from point A to point B, and how does that compare to different standards, or how does that compare between different scenarios? And so these I would call the traditional output from these models, but in response to COVID, we might want to understand what are different metrics. These don't tell the whole story as it relates to how people are going to use the buildings after the pandemic. We don't want to be designing everything to level service F, for example, if we know we want to maintain a 2-meter distance. And so the new output that we can start to look at is, first of all, trying to understand the distance that people keep between each other, or their ability to keep a physical distance. This I've seen referred to as a proximity analysis. And a lot of the software packages have started implementing this recently in response to COVID, understanding that this is something that people want to actually quantify for their designs. We can also look at the total duration that people spend in different areas of our design or of our building. So the first one we can start looking at is how long does every person spend within close proximity to any other person? Sort of a follow-on from that is how long do they spend within close proximity to specific people? The only reason we might want to differentiate those is it could be quite different if I spend 10 seconds within close proximity to 6 different people versus a minute within close proximity to one specific person. And so I'm not sure why we would want to differentiate those, but if we do need to down the road in response to some specific metric, then the modeling could look at those 2 different scenarios. And then the last one I mentioned here is we can start looking at how long do people spend within areas of high risk, and how we define high risk. That could be an area that has a very high level of congestion. It could also be an area where we've identified, perhaps through a mechanical consultant, they've done an analysis on the ventilation. We might understand that there's an area of high risk just based on how that air is moving through the space. And that's one thing I've been seeing more and more of, is that it's not just where you are in the building, but it's the actual quality of the air in that building. So it's a team approach. It's not just pedestrian modeling on its own, it's pedestrian modeling amongst many disciplines that can inform these strategies. And so this here shows a sample workflow. So on the right, we have different software packages used for pedestrian modeling. The one that we use the most at Intuitive is Mass Motion. That's what I'm going to be focusing on for this presentation. But that's just one option. I've listed a couple other, and there's many more that aren't listed here. How we actually build that model. The preference is always to start with a BIM. If we already have the Revit model on that job, it doesn't make sense to start building geometry from scratch. That's really inefficient. We should be making use of the data that we already have and using that to feed into our models. However, if we don't have that, then we can build the models from scratch. We can either assemble those from different 2D floor plans, or even starting with a sketch, we can make a very high level model. And it's not going to be a perfect model, but it's enough to at least start comparing different schemes and understanding at a high level, how does this scheme compare? Or how does it perform relative to other schemes? So this is a sample workflow. The one that I want to focus on for this presentation is one that we've developed in-house, which is really taking this and adding a middle link. So adding some sort of scripts, whether it's API in Revit or the API in Mass Motion, and automating this process to create efficiency. So the first one I want to look at is how do we actually build the geometry of that model? So this is our workflow that we've created here. So we start with the architectural BIM. A lot of programs, they will allow you to import a Revit model, but the challenge there is that there's just so much information that when you import that, it's almost too much information. It's hard to actually navigate that model, and the model actually gets quite bogged down when you go to run it. And so what we did was we took this architectural BIM and we came up with a workflow that allows us to pre-process that using the API in Revit. It basically strips down that BIM and it figures out what are the actual elements that we need for the analysis. For example, we don't care about the facade. We don't care about fancy sculptures that are within the model. We just want the baseline geometry that people actually walk on. And so this pre-processing basically gives us the rooms, the corridors, that gives us stairs, elevators, doors, just the baseline geometry that we actually need to build an analytical model. We then take that pre-processed information and we can directly export a mass motion file from Revit. And so as you can see here, it's not glamorous, but it's basically a functional analytical model that allows us to run something very efficiently and understand how does our design perform. The other benefit here is because we have our mass motion model actually within Revit, that allows us to see if there are changes in the architectural model, how does that compare to what's actually been modeled analytically. We can then look at those changes and decide if it's worth spitting out a new analytical model and running that to see the performance of it. The other benefit of this workflow is you can see every room has a little green square. Essentially what this is in our analytical model is a portal. And that portal allows us to spawn people in that room, or it allows us to make that room a destination for people to move to and from. All to say that because that's coming directly from Revit, we can name that within the Revit model, and then we can tie that back to the input for the model. So it makes creating the input that much more efficient as well. We can run this multiple times. We can look at many different scenarios. We can compare those different scenarios and see how they perform relative to each other. And then once we have the final model that we're happy with, then we can go back and grab the full geometry and import that just for visuals. But really, it's the iteration that we're doing with this slimmed down model that allows it to be more efficient. And so that was the workflow going from BIM to geometry, running the model. But really it's not a one-way street. There's feedback between here because we can also use these same scripts to then extract information from those models that we've made. And so what I want to look at now is how we used, in particular Python, but it could be any programming language, but how have we made this a two-way street such that we can create the input for the model, but then automate that process of extracting things from the model. And so on the input side, this is an example of a transit building we were working on. What you're seeing on the left here is basically the allocation of when people arrive on a train, what exits are they going to? The colorful arrows basically show a quantity of people. And so, for example, we can see in train car 7, there's 118 people that want to find their way towards the north exit. Because we've made this input parametric, what's quite powerful is we can basically change these on the fly and do a sensitivity analysis. Just make sure that our model is not overly sensitive to the first input we put in it, but really test a range of scenarios. And in that sense, start looking at trends in the model rather than the output from one specific run. Now, this is especially important as we start looking at modeling things post-COVID, because we're not going to have a clean set of input. We are going to have an idea of input, and then we can test those ranges and start to get trends and patterns from our model, which we can then use to inform our mitigation measures. If we also look at the model output, so we work within the analytical model, we calibrate it, we look at the visuals, we make sure that it's performing well, but then at some point we have to extract the data from that, and we use that for presentations or for reports, or even to compare different options together. What we've seen in the past is that this is extremely time consuming. For each graph, you're manually extracting that data from the program and then formatting it in Excel. And so what we've done is come up with Python scripts that basically allow us to automate this entire process. To give you an example, on one recent transit project, I believe we had, for one scenario, we had 25 histograms, 25 of these population graphs, and 50 density graphs. So that's 100 different pieces of output that in the past somebody would have had to manually extract, format, and interpret from the program. By automating that process, we basically hit a button. That's not instant. We usually let it run overnight to create 100 different pieces of output, but it automates that such that we can come back and we already have all of this. What that script is doing behind the scenes is taking the raw data from the model, summarizing it in CSV files, and then importing the CSV files into Excel and formatting those graphs for us. And then we can come back and we have the output, and we can then do the actual engineering work, which is analyzing the output and comparing different measures. Another thing we're looking at is how do we actually get the input for these models, specifically when it comes to physical distancing. If we look at models in the past, those have been calibrated based off real-world observations and data from real buildings. But the issue we're facing now is if we're telling people to maintain a 2-meter distance, that's a scenario that we've never actually collected data for, and it's a scenario that we've never validated our models against. And so what we've been looking at in collaboration with Blue City, this is a startup based out of Montreal that's using LiDAR to collect data. It's just an example of one intersection. They've set up a camera in this corner, And that LiDAR camera basically allows them to capture vehicle, bicycle, and pedestrian movement, and not only capture it, but figure out the velocity of people and the distance between different people. What we can then use this information for is, as I show on the right, basically try to come up with some distribution for how much space people want to maintain. What I've done here is taken the output from their video and just summarized for every person in this model what is the minimum distance they want to maintain to every other person. The challenge is you discount families because families, of course, don't need to maintain this physical distance. But all to say, we can use that data to come up with this input for the model. And we can then, when we build our model, say that every person in that model wants to follow this distribution of physical distancing. And then what we also need to do is, once we build that model and run it, take the output of that and compare it back to what we've observed to make sure that it is performing properly. This image on the right it's a very small sample size, so I wouldn't use this for actual models. This is more proof of concept to say if we have a good sample size, then we can actually build the required input for these models and test physical distancing scenarios. And so what I want to look at now is just going through different opportunities and the sorts of output that we can get from pedestrian modeling, which might inform our return to work strategies. First one I'll look at is transit. So this is an example of an existing transit model that we had. Just for the purpose of this presentation, I basically threw out the actual data that we used on the project and came up with some sample data to run different scenarios for. But in this case, we're looking at, if we start with, say, 20% of our baseline, we can see that this image here is our level of service. If you remember from before, dark blue is a very good level of service in the sense that there's very few people there, very low congestion. And so we can see at 20% of our baseline, which might be, for example, today's volume, there's no real challenge areas. There's just such a low volume of people that there's no large areas of congestion that are of concern. However, what we can use these models for is to start ramping up our passenger volume. And so we can run it for 40%, we can go up to 60, basically take this through all the way up to our full baseline capacity and start to understand as people do return to transit, at what point in time do we start getting areas of concern, which we might identify as areas of high congestion. And so if we just go back, you can see at 20%, no areas of concern. When we hit, say, 60% of our baseline, we start seeing, for example, a queue in the bottom right corner. And what this can then be used for is to inform different mitigation measures in this corner, but also when those are going to occur. We can combine this with the forecasting to understand when do we hit 60%, and in that case, when do we have to introduce some mitigation measures for this specific area of the station. So in this sense, pedestrian modeling can inform areas of crowding that might be a concern as ridership returns to our pre-pandemic volumes. We can start to understand, if we do redirect passengers, what is the impact of that, and how do different options compare to each other? And then what is the impact of changing schedules, whether it's intended or not? And what I mean by that is it could be new schedules imposed by the transit agency, and they might be rescheduling their trains, and that has an impact, obviously, on how people move to the station, just based on how those trains overlap with each other. Or it can be an unintended schedule in the sense that people themselves start taking different trains just to try and travel off peak. And those are all things that we can then inform or quantify in the model to inform our different mitigation measures. Keeping with transit, this is that same model I showed before, where it's a specific platform with construction staging happening underneath. In this case, I wanted to look at if we do introduce social distancing, what is the impact of that, and what is the impact relative to different passenger volumes. And so similar to before, we're going to start with a very low passenger volume, say 25% of our baseline. And then I've also introduced different social distancing preferences. So the blue line is 0 meters. In this model, we're not telling the passengers to maintain a distance. This could be thought of as pre-pandemic scenarios. But then we also want to look at, what if we actually told them to keep 2 meters from each other? Or what if there's some intermediate points between there? And what we can start to see is, if you don't have any physical distancing, and in this case, the train clears in just below 3 minutes, or the platform clears, I should say. But if we're telling people to maintain 2 meters, or if people themselves are choosing to keep 2 meters, in this case, we might be doubling our platform clearance. We can also look at the time and proximity map. So what this image here is showing is similar to our level of service. It's identifying areas where people are in very close proximity to each other for long periods of time. So blue and white, we don't have people in close proximity. But if we contrast that with the red, then this is telling us we have people in close proximity for a long period of time, potentially a risky situation that we want to look at mitigating. What this graph tells us, though, is even though we've told people to maintain 2 meters, that 2 meters is a preference, whereas the available space on the platform is a very real physical constraint. And so the challenge here is trying to find the relationship between those two. We have a preference to keep 2 meters, but a very real physical constraint that means we physically can't keep that 2 meters. What we want to make sure of is that what we're suggesting people do is actually realistic. There's obviously going to be a little bit of concern if we're telling people to maintain 2 meters, but they step off the train and they physically can't keep 2 meters. There's a disconnect between what we've suggested and what they can actually do. And this only gets more pronounced as we ramp up our volume. So if we look at 50% baseline volume, for example, we can see it takes a little bit longer to clear the platform. But more crucially, we have more areas of the platform where you physically can't keep that 2 meter separation. And then when we're back up to 100% baseline volume, again, we have that much more area where you physically can't keep a 2 meter distance. And not to say that's an issue. It might be okay if you have face masks and you're only there for a short period of time after you exit the train. But this helps identify areas where we can't actually keep that 2 meter distance. And we want to make sure that that's compatible with what we've asked people to do before they board the train in the first place. And so just comparing these 3 options, we can see as we ramp up from 25% volume back up to 100%, we have more and more areas of the platform where you can't maintain a physical distance. Just something to keep in mind as we're quantifying how we might return to work and different mitigation measures being introduced into these transit stations. And so what pedestrian modeling can inform, as I said, platform clearance times with or without physical distancing. And I've put an asterisk because, as I mentioned before, we haven't yet validated our models extensively for physical distancing. It is a brand new sort of behaviors that we're trying to introduce into our models. We can also use pedestrian modeling to inform the train headways based on how long it takes to clear a train. And then if we combine how long it takes to clear the platform with how many people can actually fit on that train, we can start to understand what is the actual service capacity. Again, balancing how long it takes to clear the train with how many people are actually on that train. And this can tie back into forecasting to make sure that our capacity matches what we're forecasting as our demand for that service. And so switching gears a little bit to commercial. So this is our own office at 200 University, downtown Toronto. What we first did was, you can think of it as a static analysis. It's looking at a floor plan and trying to understand how many people can we fit in this floor based on that 2 meter separation. And so the first thing we did was we sort of broke our office into 2 different teams. So here we have green team and blue team. And the rationale here is if we alternate weeks, so green team works on week 1, and then week 2, they work from home, whereas blue team is then in the office, we alternate the 2. And by alternating those 2 teams, we can maintain that 2 meter separation. So that's how we figure out the desk capacity. We then look at meeting rooms and we try to figure out what meeting room capacity can we have, again, keeping in mind that 2 meter distance. And then we've also introduced a one-way corridor, again, going back to trying to mitigate people passing each other throughout the day. And we're quite fortunate that if you look at our office, it lends itself perfectly to the circular floor or the circular flow. It's basically a loop that goes around the core. For more complex floor plans, that it might be a little bit trickier, and you could have multiple options for how you might lay out these one-way corridors, which is something that pedestrian modeling can help inform the difference between those 2 options, or the range of options. And so the first thing we wanted to do was look at the office itself, the office floor, and just understand what impact do these one-way corridors have. And so in these 2 models, we have people arriving for work over a random period of time in the morning. And then throughout the day, they're randomly going to go to the washroom, go to the kitchen, or go to a meeting room. And we can then compare the 2. So in this model on the left, this is the original office. No mitigation measures here except for the 2 teams, green team and blue team. Whereas the model on the right, we've introduced that one-way corridor. And so anytime you want to move somewhere in the office, you have to follow that one-way flow. So the visuals, as I mentioned before, they help to understand what's being done in the model. They also help to identify if it's working properly or not. But we always want some metric that we can compare between options. And so in this case, the metric we looked at is we've summarized for each option, how long are people within close proximity to each other? Or what is the average time for each person they're in close proximity? And we look at that for different distances. So on average, how long are people within 1 meter from any other, from 1.5 meters, 2 meters, etc. And this is cumulative. So anytime you pass somebody within a meter, it's going to figure out what was the duration and then add that to the time for that person. But most importantly, what we can see here is we can actually quantify what was the impact of that one-way corridor. So we have the baseline condition shown in gray, and we can see just by introducing that one-way corridor, On average, we have less time in close proximity. And so we can see that that mitigation measure actually had some impact. And if we had multiple mitigation measures, we could come up with the same sort of graph just to understand what was the impact of that mitigation measure. And if we have multiple measures, what is the relative impact for each? And is there a preferred option? We then looked at the lobby. As I said before, the challenge with lobbies is the elevators. Their capacity in many ways limits how many people can actually get to and from the floor. And that's also where we see most of the congestion. And so we have two models. The one on the left is the original lobby. The one on the right, we've introduced some queuing, which you see here. And we've also introduced designated entrances. So you can only enter the lobby from this revolving door, and you can only exit from the far side. By introducing this mitigation measure, in this case, we want to look at the time and proximity map. And what we can see quite clearly is that without any sort of structured order to that lobby, we have quite a lot of queuing directly in front of the elevator. And that can be thought of as a risky situation because you do have that large crowd forming at the base. By introducing the queuing and by introducing a one-way entrance, or a single entrance, I should say, we can see that we've taken that large queuing at the base of the elevator and we've been able to basically spread that through the lobby. The challenge here, though, is you have to look at your specific building, try to understand how quickly are people arriving or in what distribution are they arriving in the morning, and do you actually have space for this queue in the lobby? So it's not a straightforward problem. But if you can model that, if you can quantify the impact, then you can see quite clearly, you can compare that back to baseline just to make sure that your mitigation measure is having the desired impact. And so for office, what pedestrian modeling can inform is the effectiveness of our mitigation measures. And we can look at crowding in common areas. We can also look at the impact of staggered start times and what sort of congestion and queuing we might expect in the lobby. And we can use all of this to compare different mitigation measures. And the last one I want to touch on is post-secondary. And this is something that we're seeing quite a lot of interest in from some of our architectural clients, is for universities, how do we actually return to class? A lot of universities are empty right now. A lot of them have transitioned to online classes. But in the fall, for example, when we return to class, we want to understand what sort of measures do we have to implement to make that safe and to make it comfortable. And so similar to the office, we can start with call it a static analysis. In this case, we're just looking at a floor plan and trying to understand how many students can we fit in a classroom safely, maintaining that 2-meter distance. And what this tells us is basically the occupancy that we can fit in that room. What this is missing, though, is the transient aspect of it. So how do people get to and from those classrooms, and what sort of congestion might we expect in the corridors? And that's where we might introduce modeling to help inform some of these strategies. And so the first model we looked at, and this is call it the original scenario. What we're going to see here is, for example, we have 7 classrooms, and they're all going to get out at the same time. And then we're also going to have students from the floor above and the floor below that are now entering their class that is in this floor. And basically, it's a shift of people between classes on the hour. The challenge, though, and what you might think of as the risky part, is that we have one stair connecting the two, and there's quite a lot of congestion that we start seeing at the base of the stair. And so what we wanted to do was start looking at different mitigation measures. We went through multiple schemes, but the final one we landed on was looking at one-way stairs and staggered classes. Just gonna make sure this is playing. And so what we're looking at in this scenario is, first of all, one-way stairs. So all of the feature stairs are one way up. All of our exit stairs are one way down, just to eliminate that cross flow of students. And what's nice about this option is because the stairs are one way down, in the event of a fire, they're still going to be one way down. We're not telling people to do something differently in the case of a fire. And that's something we have to consider as well, is how do these mitigation measures map into life safety, and how do they relate to code requirements? But in this case here, as I said, we have one-way stairs. We also have staggered classrooms. In this case, I've only had, I think, a 2.5-minute stagger between classrooms just for the purpose of this model. But more realistically, that might be a 15-minute difference or a 30-minute difference, just to make it a little bit more realistic for scheduling. But you do have to consider this in conjunction with the university to make sure that you can actually schedule classes and make sure you're actually capturing how do they intend to use this building. We can model any mitigation measure that we want, but we have to make sure that that's realistic and actually fits what the client is expecting of the building. And so the visuals, like before, visuals are nice, they tell the story, but really we want some metric. And so in this case, again, we're looking at time and proximity maps. The image on the top here is the original scenario. As we saw in the video, there's quite a lot of congestion at the base of the stair. And once we introduce the one-way stairs and the staggered classes, we can see that we've mitigated that large crowd. But in this case, we've introduced more crowding in this corridor. And so there was a knock-on effect. We fixed to this crowding, but because we have staggered classes, there's more counterflow in this stair, and that, in that sense, we have more interaction with people within that corridor. And so this is just to point out that we can capture the impact of mitigation measures, but crucially, we can also see if we do introduce a mitigation measure, what is the knock-on effect? Because it's not always obvious when we're just coming up with these measures on paper. And so for post-secondary, what pedestrian modeling can inform, we can look at one-way corridors and stairs, try to figure out the effectiveness of those and the impact, but also the knock-on effect if it has a negative impact somewhere else in the building. We can look at the impact of staggering classes, and then for any common areas, we can start looking at what is the congestion and crowding throughout those areas, and if we have some sort of queuing strategy, is it effective, and what is the knock-on impact of that? So hopefully these examples have showed you that there are opportunities for pedestrian modeling. I think what we've seen, basically any news article that you look at, you can see that there is a strong desire to return to work and remobilize our cities. And this, I would say, is both a social desire and an economic desire. We also know as an industry that how the public uses, how they interact with, and what they expect of our buildings, this is going to change once we start returning to work, and it's going to continue to change. Expectations 1 week from now as we return to work are going to be very different from expectations a year down the road. We want to make sure that our designs and any modeling that we're doing can basically react to that change in expectations and be resilient to future change. And hopefully what you've been able to see throughout the examples is that pedestrian modeling is a tool that we can leverage as part of a broader team. And what that allows us to do is to quantify, to test, and to compare different mitigation measures as we return to work and as we remobilize our cities. And based on everything I've seen throughout the industry, I'm confident that we as an industry can help to get us back to work safely and comfortably. And so with that, I would love to take any questions.
Matt, this was a great presentation. I learned so much. I don't see any questions in the Q&A window. Perhaps we have some of the folks who are just probably typing in their questions, but for those of you who are here, definitely look for the Q&A panel. It should be located on the right side. And go ahead and type in your questions if you have any questions for Matt or myself. Now is the time to ask. All right, so no questions so far. Matt, is there any last words you want to close off with, or?
It's a pretty open-ended question. I think one thing I would say is that, we thought there would be a lot more modeling opportunities and demand in the immediate response to COVID. I think what we're seeing is there's, I haven't seen too many clients actually modeling the very first things that they're implementing. And what I mean by that is we're basically doing everything and anything to make buildings safe, which is fair and it's justified. I think what we're going to see more of, though, is down the road as we start to ease some of these restrictions. We actually want to understand, what can we safely roll back from our mitigation measures to, hopefully improve the business aspect of these buildings while still maintaining the safety. So I think we're going to see more trade-offs between mitigation measures and efficiency down the road, whereas now it's purely the focus is on safety, which is understandable.